Okay, I'm going to present some work we've conducted on an in vitro approach to perform screening of different endogenous, exogenous enzymes and applied on different ingredients to see if we could improve digestibility in pigs and poultry. To do that, we used the in vitro method from Boysen and Fernandez, which we adapted to be used into a non-com fiber analyzer that allowed us to use much bigger samples. We could use up to 20 grams of samples in each incubation time, so we could recover quite a lot of residue and then perform many more analyses. We could analyze for dry matter, nitrogen, NSPs, starch, amino acids, and also to conduct fermentability studies on these residues. So what we used is the ileal digestibility method, and we used the pig method as described by Boysen and Fernandez, just a scale to be used in the system. This consists in an incubation of 6 hours with pepsin, simulating the gastric digestion, and then this was followed by pancreatin for 18 hours, simulating the digestion in the small intestine. So this would give an approximation of the ileal digestibility pigs. We also used an adaptation of this method to simulate poultry digestion, which is essentially the same. It's the same incubation. The temperature is a little bit higher because the poultry have higher temperature, and then the incubation time of the small intestine is a little bit shorter in time. And this is an adaptation of Gigani, which is the same method adapted. So, as I said, this allowed us to measure digestibility of dry matter, nitrogen, and starch and NSP, etc. And we also conducted some fermentability studies. So we tested this with different enzymes and different ingredients. So what we tested, it was a total of 6 enzymes. It was beta-glucanase, a chyanase. This chyanase had some beta-glucanase in itself as well. It was a combination of beta-glucanase and chyanase, alpha-galactosidase, beta-mannanase, protease, and phytase. And we used that on different ingredients. We used barley, wheat. We had extruded barley and extruded wheat as well, wheat pollen or millings, DDGS from wheat and from maize, and peas, soybean meal, rapeseed meal, sunflower meal. And we also did a simulation of feed mix, which I'm not going to present results on, but we also conducted some. Altogether, we had 53 combinations that we tested with the pig model and 40 combinations that we tested with the poultry model. We used, for some of the enzymes, we used different doses. We used the alpha-galactosidase here in red. They were tested only with the pig model, and the high dose of protease was tested in the pig model as well. So I'm going to present the results of the ileal digestibility in this format. We have on the top a graph for the digestibility of nutrients for pigs, and on the bottom a graph for digestibility in poultry. And here we have a control without any enzyme. Then with the different enzymes are, in this case is beta-glucanase, protease, and this would be a control with extruded barley, and this is extrusion and beta-glucanase. And I'm highlighting only the digestibility values that they are significantly improved over the control. So this means that, for example, for dry matter, the combination of extrusion and beta-glucanase was significantly improved over the control. And then there was a tendency as well for the extrusion of both extruded treatments for improvement of starch digestibility. That's with the pig model, and with the poultry approach, we also see improvement of extruded cereal, and then protease also showed an improved dry matter digestibility and crude protein digestibility. Beta-glucanase also improved digestibility of NSP fraction for the poultry approach. Moving on to wheat, this is again the same type of graph. In this case, we tested beta-glucanase glucanase and xylanase, and significantly improved digestibility of starch when we extruded wheat. For NSP, we also saw improvements with beta-glucanase and xylanase and with extrusion. In the poultry, we saw improvements in dry matter digestibility for all approaches, both beta-glucanase, xylanase, protease, and extruded treatments, and crude protein the same, and also for starch, and for NSP also there was an improvement when beta-glucanase and xylanase was added. That's with milling, with pollen, we didn't see any effects on this in vitro approach for any of the nutrients tested, for either beta-glucanase and xylanase, or protease, either for the pig simulation model or for the poultry simulation. With the wheat DDGS, we did not see any effect either for the pig model, and for the poultry model, we only observed an effect of beta-glucanase and xylanase on the NSP fraction. For the maize DDGS, here the treatment is beta-glucanase, xylanase, protease, phytase, and the combination of phytase with the beta-glucanase and xylanase. And we said that when we added the phytase, we observed an improved digestibility of dry matter. For crude protein in the phytase itself, there was a tendency for improvement, and also for the NSP fraction, it improved with two phytase treatments. In the poultry model, we see again an improvement in dry matter and the tendency to improve crude protein digestibility with the protease, and also with the phytase we see improvements in dry matter digestibility and also the crude protein and the NSP. For the peas, in this case, we tested alpha-galactosidase, and we tested, in the case of the pig model, we had a recommended dose and a 100-fold overdose, and then we tested protease. With the poultry, we only tested the 100-fold overdose. So we see that the alpha-galactosidase, at the high dose, improved dry matter digestibility. These tended to improve crude protein, improve starch digestibility, and improve NSP digestibility. There was no effect of protease for the poultry, for the pig, whereas for the poultry, protease improved dry matter digestibility and crude protein digestibility of pigs. Here we did not see an effect of alpha-galactosidase. For soybean meal, here is again the same treatments. We see that there is an improvement in crude protein digestibility with the alpha-galactosidase high dose in the pig model, and then in the poultry we see improvements for both alpha-galactosidase overdose and protease for dry matter, for crude protein, and also for NSP with alpha-galactosidase. For rapeseed meal, we did not observe any improvements in digestibility for the pig model, whereas for the poultry, we observed a tendency with the protease to improve crude protein digestibility. And for sunflower meal, we did not observe any effect of the enzymes for the pig approach, nor for the poultry. In this case, for sunflower and rapeseed, we also tested beta-manganase, which we didn't have any positive effects. So this was the ileum digestibility results, and then we also took the indigested residues. After part of it we analyzed for these different nutrients, and another part of it we used to test the fermentability of these to simulate what would happen in the large intestine of the animals. So what we did is to take the undigested residue, with the 1 gram, and we incubated that in a basal medium without glucose or without nitrogen, together with pig, either pig or poultry, ileal contents. I mean the pig residues with pig contents and the poultry residues with poultry contents. So we incubated that together, and we incubated that for 48 hours and measured the increase in pressure inside the bottle, and we recorded that as the pressure as a measurement of gas production or fermentation. We also, at the end of this incubation period, we collected sample of this microbial incubation period, and we did some deep sequences and analysis of the microbiota, and we tested to see how the residue affected the composition of the microbiota with the liquid approach. So these are the results on the gas production, and as you can see here, that's for barley. With the pig approach, I mean, we had much lower digestibilities, and we think that not all the starch was completely digested, so that's why we have such a big difference in the fermentation here. But as you can see, there is an increase. For example, here you can see with the control in the poultry is much clearer that when we add the different enzymes, and mainly when we add the extrusion, the gas production is reduced with the addition of the enzymes. With the pig, here it's not as clear, but you can see that the extrusion plus, but the fermentation is lowest. That's probably much clearer here with the wheat, and you can see the two extruded treatments, the gas production is much lower than the other three treatments with the raw wheat. For wheat pollen, there was not a lot of fermentation going on. It was at the very end, there was a slight increase with the beta-glucanase addition. And here again, you can see that the largest, the more production is with the control without enzymes, and then the addition of enzymes reduces slightly the gas production. With the wheat DTGs as well, you can see here it takes quite a long time to start the fermentation, and also again you can see with the control it's much higher, more fermentation than when enzymes are added. And with the poultry approach, this is having no difference. For the maize, it's the same. You can see with the both of the pig, there's a slight increase with the phytates, and with the poultry, it's hardly any difference. Soybean meal, again, with the alpha-galactosidase seems to encourage a little bit of fermentation with the pig incubation, and here with the poultry as well. It looks like alpha-galactosidase might help to fermentation. Rapeseed meal is hardly any different, and sunflower meal is hardly any difference either. So this is and here's the peas, again. Peas, they have also quite a large starch fraction, and that's why probably the poultry approach gave much higher gas production than the pig. But the pig as well, here you can see that the control is also ferments more than when the enzymes are added, since to reduce the fermentation. Okay, so when we finished this, we collected this, we studied the microbiota, and here there is a study. This is for the ileal digestive pigs, and we did not see an effect on the microbiota, at least on the diversity for the different enzymes, but we saw an effect, or we can see here an effect of the different ingredients. Here, for example, what we can see is that the maize DDGS is the ingredient that gave the lowest diversity of different types of microbial. Okay? The lowest diversity is with the maize disease, and also then wheat and barley. You can see wheat here in red, and barley in red, sorry, and wheat here in brown. They are quite low, but when we extrude wheat and barley, we increase the diversity. So extrusion seems to increase the diversity of the microbiota in wheat and barley, and then this maize disease, which has already been fermented, results with the lowest diversity, which also makes some kind of sense. The same here, this is the similarity. In here, this is plotted, there is a group, these are all the treatments of different ingredients that contain protease. So for what I said, there was an effect of protease, not for the other enzymes, but for protease, there seemed to be an effect on the microbial profile. So this seemed to kind of deviate from this, the rest of the treatments without protease. And then for ingredients, there seemed to be a tendency to group together. So, for example, the peas, that's without the protease, they seem to group together here. The wheat disease also seem to go together. Sunflower meal, rapeseed, and then maize disease also seem to do. So there's kind of an ingredient effect on the microbiota. When that's for the deep sequencing at the final level. So we can see this is for the pigs. There is mainly firmicutes, and only there are some protobacteria that this is for the treatments where protease is included. There seems to be an increase of the protobacteria. So the enzyme has an effect on this particular microbiome. When we go at the genus level, here we can see that, for example, for barley, these are barley treatments. There seems to be an increase in orange. You can see that there is quite a large, substantial proportion of Enterococcus. So it seems that barley can encourage the growth of Enterococcus in the large intestine, or in the ileum, probably, because that was ileal contents that we inflated this sample with. For the peas, the treatments with peas, there seems to be also a particular increase of the residuria. And as we said earlier on, the protease seems to increase the enterobacteria and the protobacteria. In here, you can see this quite clearly. This is for the poultry. In the poultry, here at the final level, what we see is there are mainly firmicutes, and also there's quite a lot of protobacteria across all treatments, but also here there seems to be a bacteroidetes increase for the DDGS treatments, both for maize and wheat, also for extruded wheat and barley, not for the raw, but for the extruded, and for soybean meal also there seems to be a particular increase for this group of bacteria. And if we go at the genus level, here we can see that's for poultry again. We observe here that's the same as before. We saw that this bacteroidetes, the bacteroides for these groups, for the DGS, extruded cereals, and soybean meal. We saw these are the barley treatments, both raw barley and extruded in this case, and we saw also that the Enterococcus increase, which is quite including with the pig results. So barley seems to encourage enterococcus somehow. And that's all. Just to conclude, so we've seen that the carbohydrases, the chilanase and beta-glucanase, they are quite efficient to improve digestibility in the cereals, mainly wheat and barley, and also with wheat, the DGS. And they are not as efficient for wheat pollen, surprisingly, which we didn't expect, and for maize DDGs, this is not quite surprising. Protease seems to be quite good, to have quite the potential to improve digestibility in poultry, but did not have, not for pigs. We don't know why of the different species, but it seems to work very well with poultry, but not for pigs, for the ingredients that we've tested. Later on, we'll probably see those in there. Alpha-galactosidase seems to improve digestibility in pigs, but only for the pigs, and also for savory meal was quite efficient for both species. And beta-manganase did not seem to be very efficient to improve digestibility of rapeseed meal or sunflower meal. As for the fermentability, the gas production, it seems to be, we saw it's much higher, larger for the poultry model, and this is probably because our model probably did not digest completely the starch fraction, so with the ingredients rich in starch, probably the gas production was overestimated. Then extrusion reduces fermentability, and enzyme addition seems to have an impact to reduce fermentability, but it's probably not as important as that. Diversity seems to be largest for the extruded cereals, and the smallest for the maize DDGS. And then the similarity and autofuse profiles, they seem to be affected very much by the ingredient type, and also in the case of the enzymes, the protease seem to have an effect.